Good morning to all of you. In previous session, we have seen discrete Fourier transform as well as inverse discrete Fourier transform. We have seen the formula for both these, that is discrete Fourier transform and inverse discrete Fourier transform, and why it is called as that discrete Fourier transform, why it is called as NDFT. Okay, that we have already seen in the previous session. Today we will be discussing two properties of discrete Fourier transform, that is periodicity and linearity. So first we'll see periodicity property. So as per the discrete Fourier transform, the discrete Fourier transform of discrete time signal x of n is represented as x of k. Okay, so it is nothing but the endpoint DFT, and it is given as per the formula as summation n is equals to minus infinity to infinity x of n into e to the power minus j 2 pi k n by capital N. Okay, so that is the formula for DFT, or you can also call it as endpoint DFT. Right. So we know that the periodic signal, as if we already seen the periodic signal when we have discussed the various types of signals, right? So basically the x of n, the signal x of n is periodic when the x of n is same as x of n plus capital N. Okay, so that means after capital N period the signal x of n will repeat itself, right? So this is for all small n, right? So if x of n is equals to x of n plus 1, sorry, n plus capital N, then the signal x of n is called as a periodic signal. It is a periodic signal. Okay, so it is periodic signal. So the Fourier transform of x of n, right, that is discrete Fourier transform of x of n is x of k. So as per the periodicity property, if signal x of n is periodic signal, then its Fourier transform, discrete Fourier transform, that is endpoint DFT. Okay, that is capital X of k, should be capital X of k. So the discrete Fourier transform of x of n is also periodic, right? So that means x of k is equals to x of k plus capital N. So again it is for all k, right? So this is as per the periodic property of DFT, or periodicity property of the DFT, right? So that means if the given signal, that is discrete time signal, is periodic in nature, then its endpoint DFT is also periodic in nature, right? So that means x of k is equals to x of k plus n. Okay, this is as per the periodicity property. Okay, so second property is the linearity property, right? So as per the linearity property, if there are two discrete time signals x1 of n with endpoint DFT indicated as x1 of k, and another discrete time signal x2 of n with endpoint DFT denoted as x2 of k, right? Then for any real valued or complex values constants, that is small a1, a2, the linear combinations of these signal, that is a1 x1 of n plus a2 x2 of n. Okay, so that is nothing but the linear combination of these two discrete time signal, as the endpoint DFT, which is nothing but the simply the linear combination of their respective discrete Fourier transforms, right? So that is a1 x1 of k plus a2 x2 of k. Okay, so that is as per the linearity property. So we have already seen this linearity property in Z transform as well as in Fourier transform. So similar sort of linearity property is there in the discrete Fourier transform. So these same examples, or you can take any two discrete time signal x1 of n and x2 of n, and you can identify their respective DFTs, right? And by using this linearity property, you can apply the linearity property to get these discrete Fourier transform of the given uh, discrete time signals, okay, having the linear combinations, right? So yes, here we have discussed two properties of discrete Fourier transform, that is periodicity and the linearity. Okay, so in next session we'll be discussing the multiplication of two discrete Fourier transforms, which gives us the circular convolution. Okay, we'll also see one example where we'll be finding the circular convolution of the given sequences, right? And how this multiplication of two DFTs will correspond to the circular convolution property of discrete Fourier transform. Okay, so that we'll be discussing in the next session. Thank you for joining this session.